Now that the overall heat transfer coefficient is calculated, the next question is how much heat transfer we have between the hot and the cold fluids in the heat exchanger. So in order to answer this question, we will use the NTU method because we don't know all the inlet and outlet temperatures, so we cannot use LMTD method. And also we have a diagram in this exercise that is giving the efficiency of the heat exchanger for the kind of heat exchanger that we have. So first thing we need to do is to calculate the number of thermal units. This number of thermal units is defined as the ratio of UA, so the overall heat transfer coefficient, and the heat transfer area that we have between the fluids. Of course, we need to take into account all tubes because all of them are exchanging heat between both fluids. And this has to be divided by C min, so the minimum heat capacity rate or the heat capacity rate of the limiting fluid. This heat capacity rate, by definition, is the product of the mass flow rate and the CP for each of the fluids inside the heat exchanger. In our case, it's a bit special because we have exactly the same mass flow rate for both fluids, and also we consider that the CP is the same for both fluids because we have air with a quite similar range of temperature in both sides of the heat exchanger. So C min is equal to C max, and we can calculate with the mass flow rate of air and the CP of air. So then, if we do the calculation, we find a number of thermal units of 2.45, and also in order to read the diagram, we need to know the ratio of heat capacity rate. This is written with the little c, which is defined as the ratio of the C min over C max, and because C min is equal to C max, we have 1 for this ratio of heat capacity rate. Now we can use the diagram, and you look for the curve that corresponds to a heat capacity rate ratio of 1, and you look also for a number of thermal units of 2.45, and you read on the diagram. From my reading, I find 0.72 for the efficiency of the heat exchanger. So now that we have the efficiency, we can use the efficiency only comparing the actual heat flux we have to the maximal heat flux that we could have. So in that case, we will first calculate the maximal heat transfer rate, and this is defined as the heat capacity rate of the limiting fluid multiplied by the maximal temperature difference that this fluid could have in the heat exchanger. The limiting fluid can be any of both fluids because we have found that C min is equal to C max, but the maximal temperature difference, if we have an efficiency of 100% for the heat exchanger, it's if the stale air will be cooled down to the inlet temperature of the fresh air, and similarly the fresh air will be heated up to the temperature of the stale air. So here we have as maximal temperature difference the difference between the workshop temperature TA and the outside temperature TE. And then doing the calculation, we find 25 kilowatts for this maximal heat transfer rate we can get between both fluids. And knowing now the efficiency of the actual heat exchanger that we are using, The actual heat transfer rate corresponds to the maximal heat transfer rate by the efficiency, and we find 18 kilowatts for the heat transfer rate we have in the heat exchanger from the stale air to the fresh air in order to preheat the fresh air that is taken outside.